Can't see your screen. Yeah, I'll just yeah, just share your screen. Brilliant. Yeah, it's coming up now. Okay, brilliant. All right. Okay, we're a minute early, but we'll start now, Selena. So please, I'll let you know if there's any problem with the audio. Okay, I'll let you know that's going well as well. Okay, so please start. Just move to full screen.
Hello.
Yeah, we can hear you. Yeah, please start and put it on full screen.
Hello, I'm Selina Hossain. I am a PhD research scholar in the Department of Applied Mathematics, University of Calcutta, under the guidance of Dr. Soumen De. Today, I will present my work, Flexural Gravity Waves in an Ice-Covered Ocean, Induced by Oscillatory Pressure in Presence of Current. Motivation. A flexural gravity wave is a surface wave that propagates beneath a floating elastic plate or ice sheet. These waves are generated when surface gravity waves interact with the floating structure. The study of wave interaction with these floating ice sheets has attracted significant interest because of its relevance in ocean engineering as well as in the science and technology related to polar and Arctic zones. Because most of the time, the ocean surface in cold regions is covered by sea ice with water flowing underneath. These ice-covered surfaces are regarded as very large floating structures which can be used as aircraft runways, ice roads for transporting vehicles, floating parking garages, and other purposes. The compressive force on an ice-covered surface is a common natural phenomenon. Usually in summer, the axial force on an ice plate occurs in the form of compression, and in winter it occurs in the form of tension. Also, this force has significant impact on wave motion. On the other hand, the oscillatory surface pressure plays an important role in wave generation. When time-varying pressure is applied to the free surface of progressive waves, it produces a non-zero energy transfer between the applied force and the wave system, which forms the basis for sea wave energy utilization devices like oscillating water column energy devices. When there is an ice cover, the energy exchange becomes more complex. In this study, we will examine how compressive force on ice-covered surfaces influence the dynamic behavior of floating ice sheets subjected to forced time-harmonic oscillatory pressure in the fluid systems in presence of currents. My presentation will cover the formulation of the problem, solution methodology, numerical results and discussion, and conclusions. Formulation of the problem. The present problem is framed in a rectangular Cartesian coordinate system with x-axis along the free surface and y-axis is taken vertically upwards. As we see in figure 1, the model consists of an inviscid, incompressible and homogeneous fluid of density rho W which covers the region minus infinity less than x less than infinity and the finite depth minus h less equal to y less than 0. And in this model, the waves are generated by a time harmonic pressure pxt which is applied on the ice covered surface. The fluid is covered by a thin sheet of floating ice which is modeled as a thin elastic plate of thickness d and density rho y. The water below the ice is assumed to move evenly with a constant velocity u in the positive x direction. So the total velocity potential of the fluid is expressed as phi xyt as given in this expression. Also, it is assumed that the motion of the fluid is irrotational. Governing equations and boundary conditions. As the motion is irrotational, the velocity potential phi satisfies the Laplace equation as given in equation 1. The boundary condition on the ice-covered surface in presence of a in-plane compressive force capital N which acts upon the ice sheet is given by equation number 2, where eta denotes the deflection of the floating ice plate, E represents Young modulus, I is the expression given as h cube by 12 into 1 minus nu square, D denotes the flexural rigidity, Q is the compressive force which is divided by rho W, and delta 1 is equal to rho I h by rho W. And Pxt is the externally imposed oscillatory pressure. the kinematic free surface boundary condition is given in equation 3, and the condition at the rigid bottom satisfies the equation 4. And the initial conditions are chosen as given in equation number 5. Here we consider that the wavelength is larger than the thickness of ice, so we neglect the ice acceleration term delta delta 1 del 2 eta del t2 in equation 2, and with this assumption, by eliminating eta from equation 2 and 3, we can derive the combined boundary condition as given in equation number 6. Now the following non-dimensional variables are used to simplify the equations, and by considering a characteristic length capital N and characteristic time root over capital L by G. Using these quantities, we have non-dimensionalized this equation, and the dimensionless form of the governing equations are given in equation 7 to 11. We will solve this equation by Fourier transform and Laplace transform method. Now, application of Laplace and Fourier transform as defined in equation 12, we can obtain the following set of equation as given in 13 to 16. And the general solution of these equations gives the transformed ice deflection as eta bar ks as given in equation 17, and the transform velocity potential phi as given in equation 18, where omega denotes omega denotes dk cube minus qk plus 1 by k tan hyperbolic h, which is given in equation 19. The solution for eta xt can be derived by successively implementing the inverse Laplace and Fourier transform. And using the inverse Laplace and Fourier transform, we can obtain eta xt as given in equation 20. Here, p bar k t minus q is the Laplace and Fourier transform of the externally imposed pressure, oscillatory surface pressure. If we take pxt as of the form fx e to the power I sigma t, then this p bar is given by 1 by root 2 pi f bar k e to the power I sigma t minus q. Thus, the final form of deflection of the ice covered surface becomes as given in equation number 21, where psi 1 and psi 2 are mentioned in equation 22. Now, the dispersion relation of the wave generated due to the oscillatory pressure in an ice-covered ocean of a running stream will be given by equation 23, where psi d is equal to psi 12 minus uk. This can be treated as the Doppler shifted frequency relative to an observer moving with the water. In absence of ice cover and current speed, this dispersion relation reduces to equation number 24, which is actually the dispersion relation of a finite depth fluid having a free surface. The phase velocity of the wave motion is given by equation number 25 for a following current and for opposing current, which vanishes if K satisfies the relation 26. Now, if we look into the integral equation 21, the for first integral denotes the waves which is generated due to the oscillatory pressure, and the second integral denotes the waves which is flexural gravity wave, and which moves with the phase speed psi 1, 2 by k. Now, from the dispersion relation, we can obtain the group velocity as given in equation 27. And in figure 2, we have obtained the group velocity of the wave motion for different compressive force Q for a following current. It is observed that as the compressive force Q increases, the group velocity decreases. Now, the integrals in equation 21 display highly oscillatory behavior. And due to this reason, we cannot evaluate these integrals by any numerical, by any conventional quadrature methods. So we will derive the asymptotic solution of eta xt for large values of time and distance x, considering the ratio x by t as finite. For calculation, eta xt can be written as equation 28, where A1, A2, B1, B2 are the integrals that are mentioned in equation 29. We have to solve these integrals asymptotically. To solve these integrals asymptotically, first we have to identify the singularities of the integrals. If we look into the integrals A1 and A2, we can observe that these integrals contain poles. and integrals B1 and B2 contains both poles and the stationary points. The dominant contribution to the steady state wave that arises from the poles of the integrands are the roots of the equation sigma plus psi 1, 2 equal to 0, which have real roots as well as imaginary roots. So we will shift the integration contour from real line to the complex K plane. And these integrals will be evaluated asymptotically using residue theorem in the sense of contour integration. Now, application of contour integration gives AJ as given in equation 31, which is the formula for the Cauchy's residue theorem, that is 2 pi I into sum of residues of the integrand at the imaginary poles plus pi I into sum of residues of the integrand at real poles if the contour is in the upper half plane, or minus pi I at the into the sum of residues of integrand at real poles if the contour is in the lower half plane. We have chose the contour in the upper half plane, and using this formula, the polar contribution of the integral A1 can be derived as given in equation 32, where alpha R1 plus minus I beta R1 are the complex roots of the integral of the denominator of A1, and KR2 are the real roots. Similarly, for A2, we get A2 is as equation number 33. Now we have to evaluate the integrals B1 and B2, which contains both poles and the stationary points. The poles of B1 and B2 are the solution of xi jk equal to, that is kx minus t minus psi j, the derivative of this equal to 0, and which can be written as equation number 35. And the poles of the integrals are same as of the integrals A1 and A2. Now suppose that Si be the stationary point of the integral B1. Then the transient part of the integral B1, which occurs due to the contribution from the stationary points, can be inferred using the formula of stationary phase as given in equation number 36. And similarly, B2 can be evaluated by applying stationary phase method as given in 37. Here in this formula, the plus minus sign in e to the exponential form is will be taken according as the function psi at that stationary point greater or equal to 0. Now we have to evaluate the contribution of these asymptotic analysis which arises from the poles of the integrals Bj. The poles of the integrals Bj are same as of the integrals Aj, and using the formula as mentioned before, we can evaluate the polar contribution of Bj. Now, if any one pole of B1 coincides with one of its stationary points, then the polar contribution will be different. Suppose k equal to gamma be such a point. Then the asymptotic contribution of the integral B1 near k equal to gamma can be written as equation number 38, which is a formula we have taken from the paper of Debnath and Rosenblatt. This situation occurs whenever sigma is equal to mod x by t. That is our angular frequency of imposed pressure is equal to x by t. Therefore, it can be concluded that eta xt becomes asymptotically infinitely large in such cases as equation 38 represents a wave whose amplitude is proportional to t to the power half. Now evaluating all the necessary components of eta as given in equation 28, we can write the asymptotic form of plate deflection eta as eta equal to eta s plus eta t, where eta s is the steady state component and eta t is the transient component. The steady state component comes from the polar contribution of the integrals, and the transient part comes from the stationary points of the integrals. Numerical results and discussion. In this section, we have graphically obtained the ice-covered deflection of ice-covered surface for large time t and distance x for different non-dimensional parameters. For computational purpose, we have chosen these following parameters, and the non-dimensional parameters are fixed at this point. Validation with existing results. In this study, we validate our findings with the results of Debnath and Rosenblatt. When the flexural rigidity of the floating ice sheet approaches 0, our results converge with the result of Debnath and Rosenblatt. Figure 3a illustrates eta plotted against x at a fixed large time t at 300, while figure 3b shows the surface elevation eta plotted against t at a large fixed distance x equal to 280 for the oscillatory pressure pxt equal to p0 delta x e to the power I sigma t. The parameters used are d and q are 0, sigma equal to 0.39 and u equal to 0.5, and we have chosen p0 as 0.1. As seen in the figures, our results are in excellent agreement with the corresponding findings of Debnath and Rosenblatt. Now we have obtained the ice-covered deflection of ice-covered surface for an arbitrary pressure fx equal to delta x. That is, in this case, we consider that wave motion is generated due to sudden impulse at the origin. Figure 4 illustrates the variation in plate deflection plotted against flexural rigidity D, compressive force Q, current speed U, and angular frequency sigma against X for fixed large T. Figure 4a shows that as the flexural rigidity D increases, the elastic plate, the amplitude of the ice-covered surface decreases. This happens due to the fact that when D increases, the elastic plate becomes stiffer and they are more and resulting in a more rigid plate that does not vary significantly. Figure 4b indicates that the plate deflection decreases for higher values of compressive force acting upon the elastic plate. Increasing the compressive force reduces the propagation speed, and therefore we can conclude that the deflection of the ice covered surface decreases for increasing values of compressive force. In figure C, we can see that as the current speed u increases, eta changes with the amplitude of eta changes. Also, for higher values of u, the oscillatory nature of the plate deflection increases. Figure 4d shows that whenever the angular frequency of the oscillatory pressure varies, the ice-covered surface deflects significantly. Ice-covered surface deflects, and deflection in ice-covered surface changes. In figure 5, we have plotted eta with respect to t for the same parameters, and it is observed that as d increases, the amplitude of eta decreases. Figure 5b shows that as q increases, the amplitude of eta decreases, and also the frequency of oscillation decreases. Figure 5c shows that the amplitude of plate deflection decreases with increasing values of u over time t. Also, the undulating nature of the wave diminishes at higher current speed. Figure 5d shows that the wave amplitude decreases as the angular frequency of the applied pressure increases over time t. In figure 6, we have plotted eta as a function of x and t for different values of flexural rigidity. As we can see in figure 6 that as the flexural rigidity D increases, the intensity and amplitude both decreases. And therefore, the number of peaks in eta decreases for higher values of flexural rigidity. Figure 7 shows the surface plot of plate deflection eta, which is plotted against both x and t for various values of compressive forces. It is observed from the figure that as q increases, the wave amplitude decreases. Also, the wave oscillates more rapidly for higher values of q. In figure 8, we have examined the effect of current speed for whenever eta is plotted as a function of x and t. We can see that as u increases, the amplitude of plate deflection decreases, but the frequency of the wave increases. Also, for higher values of u, the oscillatory behavior increases. Figure 9 shows that as the angular frequency of the applied pressure increases, the amplitude of the plate deflection does not vary significantly, but the frequency and the wave changes. And the number of peaks in the resulting wave increases for higher values of sigma. Now in figure 10, we have plotted eta for 3 different types of oscillatory pressure. E to the power minus x square by 2, which represents a Gaussian type pressure distribution, e to the power minus mod x, which represents a exponentially decaying pressure disturbance, and delta x, which we have considered before. From both the figures, in figure 10a and 10b, we have plotted eta as a function of x and function of t. Both figures reveal that the ice-covered ocean experiences most significant deflection when the external pressure is of the form Gaussian type. Also, the oscillatory behavior of eta is found to be significantly influenced by the arbitrary function effects of oscillatory pressure. Conclusion. This slide shows the conclusions of our present study, and our present study aims to assist in solving generation problems caused by time harmonic oscillatory pressure, which is related to ice-covered ocean. And the mathematical techniques used here can be applied to simplify oscillatory integrals that arise in various problems involving the hydroelastic analysis of marine structures. These are the references, and thank you for listening. Thank you so much.
Thank you. That was really interesting. It's a really, really difficult problem you've solved there. Is there, I mean, anytime you get outside the frequency domain solution, that difficulty goes up by an order of magnitude. You know, you've got to have the transients and all that. Is there any questions?
Yeah, can I ask question?
Definitely, yep.
Yeah. So, Selina, did you consider wave and current in same direction, or they are also in opposite direction? Because as I understand, your wave and current are in same direction.
Yes, we have considered wave and current in the same direction.
Yeah, okay. That's why means if you consider this counter current effect, then you will have more than one route possibility. Means that becomes more complex. And another thing, you have used this Laplace Fourier transform, but once you consider that time is harmonic, I don't think this Laplace transform is necessary. In the beginning, if you consider this e to the power I omega t, px e to the power I omega t, then your Laplace transform is not necessary. You can think of that.
Okay, I will think of it.
And another thing, your current is co-current, this. Okay. And compressive, yeah, there is another slide. In group velocity, you have shown Q 2.5.
Yes.
But if you see at the Q2 root T, already there is an instability appears. So it's not reasonable to go beyond of this. Means you will not get anything if you cross this Q2. So better to consider Q always less than 2. Okay?
Okay. But I have drawn the figures taking the values of Q as 1.5, which is less than
9.5. I have seen that. Yeah. No, I just mentioned you because once you cross the instability phenomena, it's not reasonable. Okay? Okay. Thank you. Thank you.
Essentially, the after that, the plate will just buckle by itself. It has less energy bent. The energy that you get, there's enough energy from the compression to overcome the bending. I just have a question, a sort of technical question. I didn't understand everything you did, but when you have the pole on the real axis, Selina, you went right through the middle of the pole, whereas normally you've got to go around one way or the other. And you can, if you add some dissipation in the system, you can tell which way to go. Like I thought that was a bit dangerous.
Sir, I can't understand. Please repeat
This
the question.
here, okay, the pole's on the real axis, right?
Yes.
So you take the integral straight through the middle of the pole. You don't go above it or below it.
No, we have considered the contour integration as we have not drawn this figure in this slide, but we have considered the contour integration which covers the imaginary poles, and also uh, and we have drawn a small contour around the real poles also. And
So you,
for these type of contours, we have used the formula as given in 31. Actually, we have not drawn the contour in this slide.
Okay, no, sorry, you're right. Yeah, because you only get half the contour or something from going above.
It's
Is
like
that right? Or...
it's like poles through the real poles. Small epsilon circle about the poles and a
Yes,
big
yes, yes.
semicircle. Actually, I did similar kind of problem, but not asymptotically. It is under review for a long time. It's with current
Okay.
and co-current, counter current, that's all. And means if Selina will go through numerical, then without asymptotic analysis, she can also get the behavior near the pressure region.
Okay, yeah, I'm just because normally you tend to have there's a causality that pushes the pole off the real axis.
Yeah,
Like normally for
that we
worries
need some
me.
dissipation, like Tatiana explained, viscoelastic plate or poroelastic plate. That cases it is okay.
Otherwise, you can get waves coming from infinity or something funny like that. You get non-causality sort of
disturbances will come.
Yeah,
because of
from
real
infinity
poles.
into your problem rather than, we should
It
only want
always
them to go.
Good to put some dissipation and the poles will not real but close to the real axis.
Let's okay, we're now you and me talking some, but is there any more questions for Selina? All right, maybe we can just discuss this one. Yeah. There's no more. Maybe Selina, you could tell us. How do you see you could extend this work? What's something you could, do next?
Hello.
Yeah.
Please.
What's
please repeat.
I'll write it in the chat for you, but how could you
Okay,
extend
I'm telling her. কিভাবে পরে তুই এগিয়ে নিয়ে যাবি এই কাজটাকে? প্রফেসর মেলন সেটাই জিজ্ঞেস করছে।
Okay. We will now I am studying the actually I am working on the wave generation problems, and the papers I have published all the papers we have calculated the asymptotic approximation of the integrals, and this can be extended in the 3-dimension also, and I have not considered this till now, but we can consider this. Also, if the stationary points are complex, then we can use the method of saddle point irrespective of stationary phase method.
Steepest descent method. You are saying.
Yes.
You can do another thing, that poroelastic plate using that Korofkin's model. Then you will not have any real roots. You will get all complex roots, and the study will be simpler, I guess.
It may be more physical in a way. Yeah, because there must be at least some small.
Because in that case, in far field, there will be no wave. Wave will dissipate just after certain distance. Okay, thank you.
Yeah, and it's interesting that you can't just brute force those integrals. I think that's really interesting, and actually, over time it gets harder. Sx gets bigger, and all right. Thank you very much, Selina.
Thank
so
you,
if you
sir.
could stop sharing, we'll move to the next talk.
Yes.